Hey guys, welcome back. So we are starting our chapter 7. This is over linear regression. So we finished up our chapter on scatter plots, and now we're going to do kind of what naturally comes next. We're going to look at lines of best fit and make models, kind of like a bell curve model, which is helpful and useful for us. It's the model is not exactly like the data, right? But it's close enough to the data that it's useful for us. Okay, so we're going to look at linear regression. So using a line of best fit. In other words, to summarize or to model our actual scatterplot data. So this example is from the book, so you can kind of read along there and you can see what's going on there. So they took Burger King menu items, and we'll look at some more, I think, of Burger King in specific tomorrow. But anyway, so we wanted to look at basically they did a scatter plot of all the menu items on Burger King, and they looked at the protein and the fat. So you can see in general, as the protein goes up, so does the fat. That's going to be because there is fat and protein. So the more meat that they have on the different items, you're going to have more fat. So it's kind of cool. The question here is that if we had 25 grams of protein, how much, if we needed 25 grams of protein, how much fat would we expect to go with that menu item? So if we go over 25 grams of protein, this black line, by the way, would be our model that we're using. It's just the y is equal to mx plus b line, right? So it looks like we would expect somewhere about 30 grams of fat. Now there's no exact menu item that had 25. Well, there was one that was close to it, but it actually had about 30, looks like, anyway, halfway between that. So 37.5 grams of fat, but our model would suggest it would be lower than that and closer to 30. All right, so one thing that we see is the strength of the association here. It is linear, so it is appropriate for us to use a correlation coefficient. We have both quantitative data with their units, no big deal there, and there's no outliers. It's going to mess everything up. So the correlation coefficient, which is an appropriate measure of the strength of the association, would be 0.83. All right, so the next thing is, like, how do we get that actual model? So the model that we use is the black line. Why would we not use the red line or the blue line? Well, the first thing is we always start at the mean point. So the mean point is this red dot here, okay? And that means we have the average protein amount, which is the X bar, and on the Y bar, like X and Y axis, would be the average fat content. So if we had a typical protein content, we would expect to also have a typical fat content. So the average of the X is always going to go with the average of Y, and that point, the mean point, is always going to be will always be the one point that we know for sure, regardless of what our slope is, right? So it's always going to go through that point, and then the only question after that is, what is our slope? Is it the red line? Is it the black line? Is it the blue line, or some line in between those two, right? So that in order to find the slope, it's actually really cool how they come up with it, but I'm going to leave you hanging for just a moment. So what we're doing is line of best fit, or least squares regression line. They're two names for the same thing, but it's talking about our model. The least squares is talking about residuals and the squares of the residuals. So let's talk about residuals. So residuals are happening when we have basically gaps between the actual data itself and our model. And that's going to happen always. We'll always have residuals. So residuals is calculated to wrap. Okay, residuals is equal to the actual minus the predicted value. So if the residual is, if the actual value is larger than the predicted, so then we're going to have a positive residual. If the actual is less than what was predicted, then we'll have a negative residual. All right, so anyway, our prediction here is so the actual point was here. Our model would predict much less than that, so we would have a positive residual because it was more than we expected, right? So anyway, it's just R is equal to A minus P. You can kind of see that, and the residual is the distance between there. So the least squares is when we take the residuals and we square them. So for instance, this would be one example of a square. So here's the actual point, here's our model, and then the residual is the distance between the two, and then we square. I'm literally making a square out of it, right? Okay, same thing here. It would be a really small square. Then we have this square here, and we have this square here, and this square here, and I think that's all that I did. Oh, no, there's one more. Okay, so technically we would take the sum of all these squares, and we want to minimize the sum of the squares. So if we went back and we looked at the different slopes here, the one that would have the smallest sum of the areas of those squared residuals would be the black line. The blue line and the red line, or any other line, would have a larger squares, sum of the squares. Okay, so we're minimizing that value. Okay, we're minimizing the squares of the residuals is essentially what's going on here. All right, and that's actually done kind of, was actually not done by the calculator. The calculator actually calculates the slope in a different method, and it's really, really cool how it does it. Okay, so the slope, okay, so what we have here, sorry, is the standardized stat plot. So we have z-scores of the fat and z-scores of the protein. So whatever our distribution is for protein and fat, like if we collapse these variables, like a marginal distribution. So if we collapsed it to just the protein, or collapse all these points to the left to the fat contents, and then we calculated the basically the mean and standard deviation and made bell curve models out of it. Whenever we divide by the standard deviation to get z-scores, we're going to be standardizing it so that we can compare an x value to a y value, like apples to oranges, because we're using z-scores. So we end up dividing by the standard deviations of the protein and dividing this over here, or y values, by the standard deviation of the fat content. So that's what standardizes it, giving us this standardized stat plot. So we have z-scores of protein, z-scores of fat content. Remember, 95% of all data points we would expect to be between two standard deviations, both there. So if we look at all these points here, we would expect 95%, and there's two of them that were outside of it. So that kind of goes with it, the empirical model, pretty well. All right, so when we have this, the slope of the standardized line of best fit is actually the correlation coefficient, which is really, really cool. So the rate of how for every x we go, how many y's can we go up, that is going to actually be the correlation coefficient, which is calculated again by the sum of the products of the z-scores divided by n-1. So that little fact there is really, really stinking cool. But that's going to be the slope of the standardized stat plot, not the actual slope from our model over here, which is back in real world units of fat and protein, not z-scores of fat and z-scores of protein. So how do you go from a standardized stat plot back to the real world? Well, if we divide it by the standard deviations to get to the z-scores, to go back to the real one, we just multiply them by the standard deviation of y and the standard deviation of x. So if I go over one standard deviation of x, whatever that standard deviation is, maybe it's like 5 grams of protein. And then if I go up, r correlation coefficient times the standard deviations of y, maybe the standard deviation for fat content was 4 grams. We don't know. So it's going to be correlation coefficient of 0.83 times the standard deviation of the fat, which we said was 4, divided by the standard deviation of the protein, which was 5. And that will bring it back to the actual units of protein, grams of fat per grams of protein, which is kind of cool. All right, fascinating stuff. Suppose we have a new student. So we're going to talk about regression to the mean. This is just a really good general concept of what we're doing. Just I'm showing it with a bell curve instead of showing it on 2 dimensions. So suppose you wanted to guess the height of the new student. Where would you start? So if we know that all of our students, or American, if it's a male or whatever, so American senior males or whatever, they are average 67 inches with standard deviation of 4, and we know nothing about this student. What would be our safest estimate? Should we guess that he's a standard deviation above the mean, or should he be a standard deviation below the mean, or 2 standard deviations, or 3? Or should we just guess, if we know nothing else about him, that he's just average height? Would that be our most conservative estimate? Well, of course it would. Just to be okay, we'll just say that he's average. So if we don't know anything else about him, we would just start at the mean here. All right, suppose we have a student and his GPA is 3.9. Okay, well, if we know his GPA is 3.9, does that have anything to do? Is there any association between GPA and height? Well, let's say that they have a correlation of 0, because there shouldn't be. Taller people wouldn't have better or worse, or we expect it to be totally random, right? So if his GPA is a z-score of 1.8, so for the x variable, that was 1.8, then the response variable, because there's a correlation of 0, that means we still cannot deviate from the mean at all. So here's our formula. So the hats mean it's a predicted value. So the predicted z-score for his height is equal to the correlation coefficient, which is the measurement of the strength between the associations between 2 variables, times the z-score for the x variable, which we're saying is his GPA. So if we do 0 times the 1.8, that's still going to be equal to 0. So we're estimating a z-score of 0 standard deviations from the mean. So we still have no better information than what we started out with when we didn't know anything about him. Knowing that he is an exceptional student does not tell us any more information about his height. So this is essentially what we call regression to the mean. All of our estimates will always be closer to the mean than the original the original X variable, like in this case, the GPA, the standard deviation for the GPA. All right, if his height in centimeters, so let's say he's from a foreign country where they use the metric system. Let's say that we know that his height in centimeters is 2 standard deviations above the mean. Then how does this affect our guess? So his height in centimeters is 2 standard deviations. Well, the correlation between height in centimeters and height in inches is going to be 1 because it's measuring the same thing, just in different units. So they're going to have different standard deviations. But when we standardize it, it's going to have the same z-score. So if there's a basically kind of like 1-to-1, but if there's a correlation of 1 where it's a perfect association, if we know he's 2 standard deviations above the mean and in centimeters, that means he also has to be 2 standard deviations above the mean in inches. So how that would look over here is we do 1 times the z-score of the x term for centimeters, which is 2, meaning he has to be 2 standard deviations above the mean, which in this case would be 8 inches more than that, which would be 75 inches. Okay, no big deal, which is 6'3". All right, what if we knew his shoe size was 2 standard deviations above the mean? Now, shoe size only has a correlation coefficient of 0.86, so it is related and pretty strongly related, but it's not perfect like the one before. So what we would do is just simply 0.86 times the 2 standard deviations above the mean, which would give us about, I think it's 1.72. So we would have to estimate that it was 1.72. Notice that our estimate is always going to regress back towards the mean. It's always going to be pulled back away from the mean unless it's a correlation coefficient of 1. So it'll never be further away than whatever explanatory variable we're using. So our response variable will always be closer and regress closer to the mean, which is our safest estimate. So really what we're doing is if we have no other information, we start out with the average, and then as we get information that has a higher and higher correlation coefficient, which means it's more directly tied to it, that gives us more and more confidence to be able to deviate from the mean closer towards the explanatory variable. So anyway, kind of cool stuff actually. All right, so regression to the mean, you can actually do this from both ways. You can do the explanatory from the explanatory, and you can estimate the y variable, or you can estimate the x variable from the y variable, because the correlation is the same regardless if you switch the order of the variables. So that's kind of cool, but that is regression to the mean. It'll always, whatever you're trying to predict, whether the hat again means the prediction, the predicted x variable or the predicted y variable will always be closer to the mean because the correlation coefficient is always going to be less than 1. And yeah, that's regression to the mean, meaning this slope here, the slope of the line of best fit for the standardized stat plot is always going to be less than 1. It can't be more than 1. All right, so that's it. So that was kind of just showing the bit of the concepts here. The next part that I'm going to do, and I might even think about breaking out into a separate video if it's too long, but I'm going to go through the guided notes. And what I'm going to do, instead of breaking this down into little pieces and putting it all together, we're going to do one example that shows you all the things that we need to know about linear regression in one example. That way you'll get a really in-depth idea of all the different things. Okay, so this is a really, really important video. The guided notes pretty much go through all of it and give you really good instructions. I typed those out. I did that for a student who was absent last year, and I liked it so much I'm keeping it, and I'm just going to give it to you guys. So we're going to go through all that together. You don't necessarily have to understand the ins and outs of how all of it works, but do go through the process, plug it in the calculator to make sure you know how to do all of the stuff that I'm doing. Then we're going to break it down into several smaller parts and do some homework over the next, I think, 6 or 7 days before we take the quiz on regression. All right, so the table below lists the distances in miles of the cheapest airline fares in dollars for certain destinations for passengers flying out of Baltimore, Maryland as of 95. Okay, so enter the data into your graphing calculator for list 1 for the distance and list 2 for the fare. So we're seeing how does distance affect the fare? So that means that the distance would be our x variable and our y variable would be the airfare. So our explanatory variable, which is the one that explains the other, or our x variable, that's another way you can kind of remember that. Explanatory has an x in it, which tells us that it goes along the x-axis. Kind of nice. So x-axis distance, and then the response variable would be airfare. The response variable is the one that we're measuring, the one that we're interested in, and trying to explain what's going on here. All right, so we want to put this into our graphing calculator. So go to Stat, Edit. If you already have list in there, you can either arrow up and hit clear, or you can clear all of your list. by going to second plus sign for the memory, and then clear all lists is the fourth option. Now I'm not going to hit enter because I don't want to have to put all that in there again. So anyway, go stat and then edit and then put in list 1 your distance and list 2 the airfare. And you can go to the end, make sure you have them lined up, and that means that you didn't miss any of the data. We want to go ahead and graph it out. Alrighty, so go to second y equals. We're going to do the stat plot and from y1 or L1 to L2 because that was our x and our y in that order, and then zoom 9 and that'll graph it out for us, which I already have here. Okay, we also want to run a linear regression to find the model. So to do that, we're going to go to stat, arrow over to calculate. The fourth option is linear regression. If you look at the 8th option, it's also a linear regression. The only difference between those two, if you notice here, is this is ax plus b and this is a plus bx. Typically, I like the ax plus b because it's like the y is equal to mx plus b format. Anyway, going from list 1 to list 2, the order of these two does matter for the x and the y list because that's how you're going to be running your equation. So we're going to store the regression equation as y1. So to do that, we need to go to variables, arrow to the right to y variables, functions, and then y1, and we're going to store it there. That's really important. So that's going to find the line of best fit and store it in our y1, and then hit calculate. Now we have our correlation coefficient. The r squared is going to be the coefficient of determination, which tells us the proportion of variability, or sorry, the percent of the variability in the y variable of airfare. So basically 63% of the variation in airfare can be accounted for by distance with the model, okay? And then the A is going to be your slope, right? Because it shows you here that's your slope. And then the B is going to be your y-intercept. All right, so let me make sure I have all those. And yeah, you totally have basically the instructions telling you how to go through that. Write the equation of the predicted cost from distance and y is equal to mx plus b format. So the airfare, we said the slope was 0.117 and the y-intercept was there. Then the next thing is we want to use that to estimate the airfare for a destination that's 900 miles away. So there's two ways you can do it. You can just plug it in the calculator and multiply it. So you can do 0.117 times the distance of 900, just like you would think, plus the y-intercept. Okay, you can do that. Or what's really nice, because we save that, if you go to y equals, by the way, it put that equation in y equals because we stored the regression EQ as y equals. And if you hit graph, you notice it'll graph the y equals line, which is really, really cool. And you can even hit trace there and it'll go back and forth. If you arrow up, you see how it changed from green to blue. See, it's graphing the plot, tracing the plot. Now it's tracing the line. And you can go over here. We could arrow over to 800 to get an estimate. What was 800? 900 that we were doing. Sorry. Oh my goodness. So an X value of 900. Okay, that's the closest we can get. So it's going to be around $188, which is what we got doing that anyway. Okay, so one thing that we can do is, and this is a really nice trick. So go to, sorry, not distribution. So just go, yeah, so go to variables, y variables, function, and y1. And then we're going to use open parentheses to evaluate the function at 900. And then you can just hit enter and look, it does it for you. The reason that we had a slightly different value is because we rounded. If we would have used all the precision, like all the precision that you see in here, that's a lot of precision, then you would get the exact value. Okay, so it is actually better to store the regression equation and evaluate it, which will give you that value right there. And we only want to use 2 decimal places because we're talking about money. We can't have less than a cent anyway. All right, so is this interpolation or extrapolation? So extrapolation is whenever we work and we predict something outside of the range, or sorry, the domain of our x values. And interpolation is whenever we're valuing within the data. So our range of values, if we look, I think I said that was from 189 to 1502. So that's our range of data. I mean, the domain, I'm using the wrong word, but you get what I'm saying. And if we're looking at 900, that's within the domain. And so this would be interpolation, not extrapolation. So we can trust the values. We don't ever want to do extrapolation, by the way. All right, what airfare would the regression line predict for a flight to San Francisco, which is that many miles? Okay, so we're going to evaluate the equation. I can actually go up here and then just change it. So that was 2842. Boom, done. So we would estimate the airfare to San Francisco to be $416.85. All right, would we take this prediction as seriously as 1 for 900? No. Why? Because this is extrapolation. Our model only had data that went up to 1502, and this is over about, more than 1,000, more than that. So we don't know how well our model works for data that's that far off. Okay, so we would not take it as seriously because it was extrapolated to get. What is the slope of the regression model for predicting the airline? Okay, so the slope was 0.117. What does that slope mean in context? So for every mile, for every additional mile of travel on the flight, we would expect 11.7 cents for our airfare to increase by that for every mile. And then what does the y-intercept mean? That means if we had a distance of 0, so if we just get on the plane, we don't go anywhere, and then we get off the plane, then we would expect that they would charge us $83 for security or whatever. So anyway, kind of silly. A lot of times the y-intercept doesn't make sense, and so we would never evaluate the distance of a flight for 0 miles. But still, you have to have that value to make the other part of it work when it's within the domain. And also, 0 is not within the domain, so it's not going to. It would be extrapolation anyway, which is kind of cool. All right, write the formula for the residuals. So R is equal to A minus B. I think I already gave that to you. Find the predicted value for the airfare from Baltimore to Atlanta, which is that many miles. You can find the number of miles that it actually is in our data because it was listed up there. So, in the table. All right, so we want to multiply that or just simply evaluate for that part. So I'm just going to evaluate it. So that's going to be 576. Oops. That would definitely be extrapolation. All right, so that's going to be $150.88. Okay, so that's fine. You also could multiply doing the same thing. All right, so if the actual airfare to Baltimore to Atlanta was that much, so it was more than predicted, so that would be a positive residual, then what is the residual value for Atlanta? So we're going to do actual minus predicted to get the residual. The actual they said was 178 minus the predicted, which we said was that. And if we subtract those two, we get a positive residual of 27.12, meaning in context that the actual airfare cost 27.12 cents more than what we expected, because it was a positive residual. All right, the residual for Chicago is negative, meaning it costs less than we expect. That's a good thing for the consumer. What's the actual airfare? So now we're just kind of working backwards. So we're plugging in the residual, which they told us. The actual is what we're going to solve for. And now we just need to find the predicted. So the predicted, we can find that by plugging in the distance, which was 612. So I'm going to evaluate it for 612. Okay, and then, so that was the predicted. Okay, then the only thing that I have to do is add the predicted to both sides to get the actual by itself, which would give me $94, which is actually what we have in our data table anyway, so that's not that impressive. But you will have to solve problems like that, just solving backwards with the residuals. All right, so what's the correlation coefficient for the regression model for predicting airfare based on distance? So the correlation coefficient, to find that, we run the linear regression, which I think we already did. So stat, calculate, yeah, linear regression 1 to 4. We don't need to store the regression in Q anymore because it's already been stored. So yeah, you can skip that now. Looks like our correlation coefficient is 0.795, I guess, if you wanted to round. So it's kind of nice I can do that. Don't know why I did it though. All right, the square of the correlation coefficient written as r squared. So in the calculator, that's going to be this r squared here. It literally is just the correlation coefficient squared. Okay, there's nothing special about that. But what it is it is our coefficient of determination. So it tells us what % of variation in the fares or the cost of the fares can be explained or accounted for by the model by the distance. So basically 63% of all of the variation can be accounted for by the variation in the fares can be accounted for by just simply the distance, but the rest of the variation is accounted for by other factors that we haven't looked at yet. So anyway, we were able to remove 63% of the variation by simply you telling me how far away you're traveling. The rest of the variation is due to other factors. All right, anyway, that's good stuff, no big deal. Okay, yeah, good. What proportion of variability is explained? We did that. According to the model, 63% of variability in airfare can be explained by the variability in distance. So you are going to be writing sentences like that. So just go ahead and commit that to memory. And the best way for you to get that down is just to be repeating that, and I'll be repeating it and repetition in the homework, okay? All right, now anytime that we calculate a linear regression, it'll automatically, because it has the original data, which is in the, from the X1, the list 1 and list 2, okay? So it's got the actual, and it knows the predicted from the model. So to find the residuals, we could actually find that. Let me go to that real quick. So stat edit. So here I have the actual, these are the response, or sorry, that's the explanatory variable. This is the actual values. So what I might want to do is find the residuals. So the residuals is going to be equal to, so I'm going to define list 3. Residuals are equal to the actual, which would be list 2, so the actual cost. All right, so list 2 minus the predicted cost. So the predicted cost, we find those by going to variables, y variables, function y1, and y1 being evaluated at the explanatory variable, which is list 1, and then we can close that. And so this is really residual, okay? So what we're calculating is the actual minus the predicted, and those will be your residuals. Now what's cool is that list is actually already calculated for you. If you go to second stat, see the little list menu, and see the resid on the very bottom. So this residual, all right, so if I do list 4 and I define that and say that that is equal to the residual list, so second stat, arrow down to residual, boom. Yeah, that's so cool. So you notice how those are exactly the same. So that formula that I just showed you, like, you know, wrap residuals actual minus predicted, it actually does that for you. So you'll never have to know how to do that. I'm just showing off at this point. All right, so we want to graph the residuals to see what's going on here, and this is pretty typical. We'll talk about this more in more depth later, but anyway, the X list is going to be list 1, and then our Y list, we're graphing the residuals. So we can go to second stat and then hit residuals there, and then do zoom 9 to do our zoom stat fit, and boom, that's our residuals, which has kind of been graphed here. So you can see this is like our model, you know, our model goes like that, but they're kind of flattening it out, and then we're just graphing out how high above or below our residuals were. So did it cost more than we expected? Those would be these points here, or less than we expected. It's that simple. And the residuals usually will say it's y minus y hat, which is the actual minus the predicted. Again, we put the hat sign symbol for a prediction, which is associated with our model, not the actual data itself, okay? All right, so sketch a residual plot, we did that. We can interpret the lack of pattern. So if we saw a clear curve here, that would mean that we were trying to fit curved data with a line. And so that would tell us that it's not appropriate, it's not linear, and we need to re-express the data by squaring, square rooting, logarithm, something like that. But we don't have any clear pattern here, so that means that the linear regression model is appropriate, meaning it was actually linear and we're good to go. So we always check residual plots. We check the scatter plot, we check the residual plots afterwards to make sure that it's appropriate. All right, so I know the video is pretty long. You really don't have an assignment. You're just kind of going through the notes, the guided notes that I had. And I wanted to give you an example of all of the things that we are going to be getting into when it comes to linear regression. So today was kind of like an introduction and just getting your feet wet and seeing what it looks like and how to put it in the calculator and stuff like that. Okay, we'll break it down into the individual days and spend more time and do actual problems from the book and stuff like that to get you used to doing all these things. Okay, so don't freak out if today was quite a bit. I do it on purpose. So anyway, I'll see you guys later. I hope you have a good day.